You know, every time you tap your screen, open an app, or even just turn on your computer, there's one tiny little component at the heart of it all, the microprocessor. Today, we're going to pull back the curtain on this brain by looking at a real classic, the Intel 8085, to see how the magic that powers our entire digital world really works. So, what is that tiny, silent brain that's running the show in everything from your phone to massive cloud servers? Well, it's the microprocessor. And here's the cool part. If you can grasp its basic principles, you pretty much understand the foundation of all modern tech. All right, here's our game plan. First, we'll tackle the big picture. What exactly is a microprocessor? Then, we'll zoom right into its anatomy, its three core parts. After that, we'll get to meet a legend, the Intel 8085. And finally, we'll get down to the nitty-gritty and see how it talks to the world through its 40 little connection pins. Okay, let's jump right into that first big question. When we use the word microprocessor, what are we really talking about? So, at its very core, it's all about being programmable. It takes in binary data, just ones and zeros. It follows a list of instructions it gets from memory. It processes that data, and then it gives you an output. This simple loop, input, process, output, that is the fundamental rhythm of literally all computing. So, how does it actually do that processing? Let's zoom in and take a look under the hood. It turns out you can boil the whole thing down to three absolutely essential parts. Yep, inside pretty much any microprocessor, you're gonna find these three key players: an arithmetic/logic unit, or ALU for short, a set of registers, and a control unit. These three are constantly communicating and working together to get the job done. Think of the ALU as the mathematical brain of the operation. It's the part that does all the heavy lifting, all the number crunching. Need to add two numbers or compare them to see which one's bigger? That is a job for the ALU. It is the absolute workhorse of the chip. Now, while the ALU is busy doing all its calculations, where does that hold the numbers it's working on? Well, that's where the registers come in. You can think of them as a super fast little bitty scratch pad right there on the chip where the ALU can just jot down numbers while it works. And finally, that brings us to the control unit. So if the ALU's the calculator and the registers are the scratch pad, the control unit is the director of the whole show. It reads the instructions and tells the ALU, the registers, and everything else what to do and exactly when to do it. It's like the traffic cop for all the data, making sure everything happens in perfect order. Okay, so that's the theory. Now let's make it real. We're going to look at one of the most important early microprocessors ever made, the Intel 8085. It is the perfect way to see all these principles in action. I mean, just look at how fast things were moving back then. The very first microprocessor, the 4-bit 4400, comes out in 1971. And then just 5 years later, we get the 8-bit Intel 8085. This wasn't just a small step up, it was a giant leap that became a cornerstone for the entire early microcomputer industry. The 8085 is an 8-bit microprocessor. Now that's a really key detail. It basically means the chip thinks and works in chunks of 8 ones and zeros at a time. This 8-bit architecture was the standard that powered that first amazing wave of personal computers. Physically, it's a 40-pin chip. And get this, those 40 little pins are its entire connection to the outside world. They're the gateways for power, for data, for all the control signals. We're going to see exactly how they work. And with its 16 address lines, it could talk to 64 kilobytes of memory. Now I know, 64K sounds like nothing today, right? Your phone takes photos way bigger than that. But in 1976, man, that was a huge amount of space to play with. All right, let's zoom in on those 40 pins. How does this chip actually plug into memory and all the other devices? I know it can look a little intimidating, but we can break it down into really logical pieces. So instead of trying to memorize 40 different pin functions, which would be crazy, we can just group them together by what they do. Some pins handle addresses, some handle data, and others are all about control signals and power. Let's dig into the most important ones. Let's start with the address bus. It's pretty straightforward. 8 of the pins, A8 through A15, are basically a one-way street. Their only job is to shout out the first half of a memory address, telling the computer system where to go look for information. Okay, now here's where the design gets really clever. To save space and money, the 8085 uses a trick called multiplexing. A set of 8 pins does double duty. For a split second, they send out the second half of the memory address. Then, instantly, they switch roles and become the two-way road for the actual data to travel on. So you're probably wondering, how does the rest of the computer know if those 8 pins are carrying an address or if they're carrying data? Well, that's the job of the ALE, or Address Latch Enable pin. The control unit sends out a quick pulse on this pin that basically yells to the memory chips, "Hey, the info on the bus right now is an address. Grab it." Then the pulse stops and the bus is free to carry data. Next up, we have the fundamental read and write signals. They're active low, which is just a fancy way of saying the signal is on when the voltage is low. So when that read pin goes low, the processor is telling memory, "Hey, put your data onto the bus for me." And when the write pin goes low, it's saying, "Everybody get ready, I'm about to send some data for you to store." And to be even more efficient, the 8085 combines a few signals to create what's called a status code. By just looking at the pattern of ones and zeros on these pins, other parts of the system know instantly if the processor is reading from memory, writing to a device, or grabbing a new instruction. It's like a simple code that describes the processor's every single move. And finally, the processor isn't just talking all the time, it's also listening. It has pins that let the outside world interrupt what it's doing. An interrupt could be a super high-priority emergency signal that just can't be ignored, or maybe a request from another device to borrow the data bus for a moment, or even just a signal from a slower part telling the super-fast CPU to just, chill out and wait for a second. The Intel 8085 had about 6,500 transistors. The processor in the device you're watching this on right now has billions. But, and this is the amazing part, underneath all of that mind-boggling complexity, the fundamental principles are exactly the same. There's still an ALU, there are still registers, there's still a control unit, and there are still buses. The scale has changed beyond anything we could have imagined, but the core ideas we've talked about today, they are absolutely timeless.